The second talk will be given by Professor Panos Patrinos. Panos is currently an associate professor at the Department of Electrical Engineering of KU Leuven. So he got his PhD degree from National Technical University of Athens in 2010. So after that, he held postdoc position at the University of Toronto and the IMT RUCA. I think since 2012, Panos became an assistant professor in IMT RUCA. And after that, he moved to KU Leuven. So Panos has a broad research interest in system theory and optimization algorithm. So he also has developed several very nice operator splitting-based optimization tool in Julia, so which is very nice. So if you are optimization started, you should try to use them at the beginning when you studied operator splitting method. Okay, so thanks again, Panos, for coming. So now give the stick to you.
Thank you very much, Yuning. First of all, for the invitation and for the nice introduction. And again, I would like to stress that it would be much nicer if we did this in person, so we could also interact together with the students. But anyway, this is the best we can get, so let's live with it. So today I'm going to talk about fast proximal algorithms for non-convex and large-scale optimization. So because the title of the session, I think it had to do with non-convex and large scale. So I decided to give a talk about that. And I will talk about proximal algorithms, and we will see what this means for those of you that don't know. As Yuning said, there is also some accompanying software that helps you implement these things or even try them out without having to program a lot yourselves. And basically, just as an outline, so before Moritz was saying, whenever you can use a direct solver or a Newton type solver, you should prefer it over first order methods like Admm. And so somebody would think, okay, now Panos is going to talk to us about first order methods because this is what proximal algorithms are about. But in fact, my goal is to bring, let's say, Newton type methods and proximal methods together. And I will put more emphasis on a global convergence analysis because local convergence, it somehow comes for free, fast asymptotic convergence, as Moritz was highlighting before. But the challenge here is to make this type of algorithms converge globally and in the non-convex setting, because most of these algorithms initially operator splitting methods or proximal algorithms that have been proposed for convex problems. And there the analysis is completely different. So here we will see how we can analyze what can we say about convergence, for instance, of Admm when it is applied to non-convex problems. Okay, but first, this is a summer school. So let me start by some very introductory stuff that I usually cover in my optimization courses in the master level and the PhD level. So what is optimization? I guess you all know it is a technology of devising effective decisions. When we talk about control, we talk about decisions, but also predictions, right? When we train a neural network or a classifier, we want to do predictions. So there are a bunch of applications. Mainly, I guess most of the people here are interested in control applications, right? For autonomous systems or also for large-scale systems where basically you have several parties or agents trying to interact and trying to collectively solve a global optimization problem. So I will not go into detail how you can do distributed optimization. Many of these algorithms lead to distributed optimization for solution methodologies, let's say. But in order to make them distributed, it is a matter of massaging your problem a bit, as Moritz showed before. Right. And of course, another major application domain is machine learning and statistics, right? And in fact, we have seen lately many people coming from the machine learning community, making a lot of nice contributions in in the optimization part, right? And of course, there you can think of training neural networks. Typically, people use backpropagation and stochastic gradient or some other solvers with momentum like Admm. And also in reinforcement learning, the same thing, right? Optimization is being used. When you do policy gradient, you apply some stochastic gradient method in signal and image processing and so on. So here is one example. When you train a neural network, as we said, so you are given a loss function, either quadratic if you have a regression problem or something else if you have a classification problem. And basically here you are given a set of data points which consists of inputs and outputs. And basically you try to fit a nonlinear model by passing these inputs through a sequence of linear and nonlinear transformations, right? So this is the output of the neural network, and you try to match it to your training data, right? And typically people, they apply stochastic gradient in the sense that they take mini batches, so capital N is a number of data, and they only, take a gradient step along only one data point based on this loss function, or more than one data points, but just a small amount and not the entire set, right? And actually, if you think of this, so basically you can also write this as a dynamical system, right? And view this as an optimal control problem, drawing a link with the theme of the summer school, right? So it is, these are the initial conditions, and then you have dynamics given by these nonlinear activation functions. And at the end, you just have a terminal cost and you don't have stage cost, but it is an optimal control problem. And backpropagation, which is a way of calculating, the derivative, the gradient of the loss function is nothing more than backward differentiation, right? Or the adjoint method for calculating the derivative of the neural network. Another application is, of course, in automatic control, and especially model predictive control. I guess you all know also Morris described before he gave a very nice introduction to model predictive control, where there the goal is basically to solve an optimization problem, an optimal control problem in real time, very quickly. And it would be nice also, if you could embed your solver in very cheap hardware, because then you can send it to mass production and make it available to devices like mobile phones or cars and so on. So there, the solvers need to have certain requirements. They said they need to be simple enough to be implemented on cheap hardware. This means that you might not want to, for instance, solve linear systems, right? Because then this is a complicated operation and the size of your code will increase, and this is difficult to verify, let's say. You also need to have low memory requirements and so on. So in some cases, first order methods might also give you good results in this, especially if you want medium accuracy and you are not interested in high accuracy solution. And also, it would be nice if you could also bound the worst case execution time, right? Because you would like to give a guarantee beforehand, before you deploy the controller, and say that in the worst case execution time, will be less than the sampling time of your system, or put it otherwise, within your sampling time, I will be able to run that many iterations. And based on this theoretical bound, I can tell you that I will give you a solution of this quality. So you can tell me what to do with the solution. And of course, when we talk about MPC, we not only talk about small fast systems like autonomous vehicles and so on. You can apply this thing, which is in fact a technique which has been applied in also in operations research for many, many years. There they call it rolling horizon, this procedure. Basically, you do a plan in the future, you optimize over this prediction horizon to compute a plan. Then you apply only the first decision, and then when you receive new information, then you repeat this procedure all over again. And the challenges here, like in this application in smart grids, is that you have a lot of stochasticity, right? So you have a lot of renewable resources like wind and sun that you cannot predict very reliably. You cannot give a point estimate which is exact. So in that case, you will need to apply stochastic MPC, and this further increases the size of the optimal control problem. But of course, it gives a lot of structure, because now, so if you have discrete uncertainty, then you need basically to solve an optimal control problem over a scenario tree, right? And there are many ways to decompose this problem, do either scenario decomposition or nested decomposition, as it is called, and so on. This is another example which is related to the theme of the summer school, right? So this is MPC for drinking water networks. Again, here you have a very large-scale system. Basically, you have a dynamical system which has hundreds of states, and you have high uncertainty. And the goal is to fulfill the consumer demands for water supply. And when we were doing this, when we were trying to solve this problem, it was for some European project together with some people from Barcelona, and this is actually the Barcelona drinking network. We ended up with an MPC problem which is huge, right? So it has more than 2 million of variables and 3 million of constraints. So then you will need to do some computations on GPUs, and it is much easier to parallelize the methods that we will describe now on GPUs rather than the ones corresponding to, solving some linear system with a direct solver. So in other words, even these optimal control problems, when you have large-scale systems and a lot of uncertainty, they can become very huge quite fast. Right? Of course, there are other types of applications of optimization, like data analysis. Right? For instance, there is this low-rank optimization problems, which have found many applications in, for instance, recommender systems. So you are given a table or a matrix where basically some of the entries or many of the entries are missing. You can think of, user ratings of different movies. So the columns correspond to different users and the rows to different movies. And of course, each user has only rated a small number of movies, right? And the goal is to fill in this matrix with ratings in order to suggest movies to other users, right? Based on their preferences on some other movies. And in fact, because the preferences of the users, they are only relying on a few characteristics, this matrix will be low rank. So it will have a lot of redundancy, right? And then the goal here is, to basically approximate this matrix. This would be an M, right? With a low rank matrix, and you can do this using several techniques. One way is this non-convex formulation, where you say, okay, I want my matrix to be low rank, so I will write it as a product of tall matrix and a wide matrix, right? And I want this to be equal to M, but not exactly M, because I only know a few elements of M. So I'm only comparing this approximation I'm only putting a penalty, of course, for the elements of M that I know. Right, so this is a non-convex formulation, and of course there exist convex formulations. And now here, the main characteristic, so X here is what? X, so suppose that this M is M by N. So X here will be, it will have many rows, but only a few columns equal to the rank that we guess, right? And the same with Y. So it will have many, not here I'm taking Y transpose, so Y will be, again, a tall matrix. We will have N rows and R columns, right? So this means that in total I have, I have M plus N times R variables, right, in this formulation. But of course it is non-convex, right? So it is a compact formulation, let's say, but it is non-convex. Now there exist other formulations where basically they say in order to achieve low rank, I will use an L1 penalty on the singular values of the matrix X, right? So this is what this norm is about. This is called, how is this called? Who knows? The nuclear norm, right? And it is basically the sum of the singular values of the matrix. And, this is like the L1 norm. So it tries to induce sparsity on the singular value. So it will try to set many of them to 0. But now here I'm optimizing over an M by N matrix. And of course, even though this formulation is convex, M times N is much larger than this guy here because R is typically small. So 3 or 4, let's say, right? So here I'm multiplying these large dimensions. Here I'm just summing them and I multiply them with a small number. So even though this problem is convex, and people were very excited when they found out that this relaxation works well under certain conditions, of course, on your data, the algorithms needed to solve this problem, so you can formulate it as a semi-definite program, or you can apply some of the algorithms that we will discuss later on. But the thing is that at every iteration, they would require a singular value decomposition of a big matrix. Whereas this formulation here is basically an unconstrained smooth formulation, and you can apply, for instance, the gradient method. Right? And people have found lately, but I will not go into detail, that this formulation is not that bad. In fact, under certain conditions, similar conditions for which this problem gives you a good approximation of the best low rank approximation of the matrix M, also gradient descent, if you apply to this problem, will also give you equally good results. But now, of course, solving a much smaller problem, right? So signal processing, this is another application. This is to show you basically that nowadays we need to solve problems perhaps with more exotic constraints than simply saying, I have a bunch of nonlinear inequalities smaller than something, right? So you could include constraints like the rank of a matrix as being smaller than R. Of course, this is a very non-convex constraint, so on. Basically now, instead of the nuclear norm, which was the L1 norm of the singular values, which is a convex function, now here we have the L0 norm, which is the number of non-zeros of the singular values. And of course, this is a very non-convex constraint. And here is the analog, not for the singular values, but for the elements of the matrix. So here we are given a matrix S, right? Basically, this is a signal. It is basically, in this application, you have footage from a video, and you take the frames and you stack them one under the other, and you obtain a huge matrix S. And you want to decompose it into two parts, one which is sparse and one which is low rank. So S should be approximately equal to X plus Y. And you would like X to be sparse and Y to be low rank. Why Y to be low rank? Because Y basically represents, we want Y to represent the background of the image, so the thing that is not moving along the frames. And since it is not moving, it is very similar across the frame, so this will be a low rank component, right? And you want to somehow identify the moving objects, which are, humans, for instance, they are sparse because, sparse in the sense that they only occupy a very small number of pixels compared to the overall image. And of course, this problem is a non-smooth, non-convex problem. And again, you know, it can become huge really quickly. So these are some motivations why, you know, some rethinking perhaps of which algorithms we should use should be done. So basically, in the classical numerical optimization, people were dealing with smooth problems without structure, so they were just assuming that you can calculate the sensitivities, the gradients, and you were given some, you know, you were writing down everything as a nonlinear optimization problem, minimize some function subject to nonlinear inequality constraints. And typically there, yes, you would use second order information, methods like sequential quadratic programming or interior point methods. And you would, you know, first you would compute the sensitivities, then you would form a QP, at least in sequential quadratic programming, and then you would pass it to some QP solver. And these methods work very, very well. Right. And the emphasis is mainly on asymptotic convergence. So when you are close enough, what can you say about the convergence rate? And of course, these algorithms converge very fast because there are variations of Newton's method for solving nonlinear equations. And the aim was typically to solve small to medium scale problems, right? Today in optimization, the aim is to solve sometimes very large problems that are still non-convex most of the times. And they are also non-smooth, right? So now we cannot always take derivatives of terms. We need to find another, let's say, proxy that will replace the derivative. And these are the requirements nowadays that people put, let's say, on a good algorithm for large-scale optimization, right? So the computation per iteration should grow nicely with the dimension of the problem, right? Linearly, let's say, right? Or even sublinearly. Because then we end up, I mean, if you end up with a problem with millions or thousands of variables, even doing operations that take big O n square, let alone n cube, like solving a linear system, might be out of the question. Of course, you know, if you have a lot of structure in your problem, then you get sparse matrices, and you can do things much faster. They should be easy to parallelize, and this is in accordance with the theme of this summer school. And typically, they take few iterations to reach modest accuracy. And some people are satisfied with modest accuracy, but in some applications, you might need high accuracy, right? And they should be able to handle non-smooth terms and, you know, consist of simple operations like matrix-free methods. And by this, I mean that, you know, you might have components in your problem, for instance, that are inverse Fourier transforms, right? This can be represented as matrices, but you will never do this in practice. What you can do is you can multiply with this linear operator or with its adjoint. And this is what you should do. You should never form these matrices, right? So that's why people, the past 10, 20 years, 10 years, they have put a lot of emphasis again on first order methods, which is a bit of a paradox because some years ago, you know, people that are experts in this community, they were saying that you should always use second order information. So in this talk, we will try to combine the best of both worlds, right? So we will try to keep the flexibility of what we call proximal methods in terms of simple operations. And at the same time, we will try to do some online scaling as we will see these Newton type methods in order to make them more reliable and converge faster. And we will see how we can guarantee global convergence by doing that. And of course, before doing that, because it is, of course, a summer school, I will provide an overview of some of these first order methods, right? And the tool that we have developed to do that is called proximal envelopes, right? So any questions so far? No, okay. So I will start with the simplest possible method. I guess you all know, and the simplest possible problem, because that's something that we can all relate and we all know about it. So when you minimize a function f without constraints and you suppose that the function is differentiable, in fact, continuously differentiable, then basically, problem becomes something which is quite simple. Of course, still, if the function is non-convex, then you shouldn't hope to compute the global minimizer, right? So the only thing that you should hope for is to find a point that satisfies some necessary conditions for optimality. What are necessary conditions? There are conditions based on first or second order information that tell you that if a point is a local minimizer, again, now we will focus on the best that we can achieve, which is a local minimizer, then the gradient vanishes, right? Such an X star is called a stationary or a critical point. A stationary point, which is not a local minimizer or maximizer, is called a saldo point, right? And algorithms, basically, we will see first order algorithms that try to find points that satisfy this condition, right? And this is the best that they can do. Of course, if we were able to verify some second order conditions, things would be even better. Right, so we have the second order necessary condition, which tells us that if X star is a local minimizer, then the eigenvalues of the Hessian at that point are non-negative. Of course, X star, if X star is a local minimizer, then of course this implies that also the gradient vanishes at that point, right? And this is a second order necessary condition of optimality. The first order one now guarantees that if you have a point for which the gradient vanishes and the Hessian has strictly positive eigenvalues, then in fact this is a local minimizer, and in fact it is a locally unique minimizer. Right. So in principle, we would like the algorithms to converge to points satisfying this condition, but perhaps this is too much to ask, and sometimes we are happy with first order, the first order necessary conditions. However, for some problems, especially lately, people have found that even first order methods can avoid the so-called strict saddle points. So again, we said that a point, a stationary point is a minimizer if the minimum eigenvalue of the Hessian is larger than 0. And this is how a minimizer looks like, right? So you have this ball-shaped function around this point. Locally, it looks like a strongly convex function. A maximizer, of course, is a point, stationary point, where the largest eigenvalue is smaller than 0. So now you have a locally concave function around that point. And a strict saddle point is a point where basically the minimum eigenvalue is smaller than 0 and the largest eigenvalue is larger than 0. This means that if I move along certain directions, I can decrease my cost, and along certain others, I will increase my cost. And in fact, there are algorithms that can take into account this second order information and can produce directions that slide down these saddle points, these strict saddle points, because of course there exist saddle points where basically the minimum eigenvalue is equal to 0, right? Degenerate saddle points. However, people have found that, recently have found that problems like that look like a low rank matrix approximation problem. So this is, you are given a matrix basically, and you want to find the best low rank approximation of it, and you can formulate it the way we said before, right? So here we are giving a 2x2 example, and I want to approximate this matrix, which is symmetric with a rank 1 matrix, and every rank 1 matrix I can write it as, as the outer product of a vector with its self, right? So this boils down to minimizing a fourth order polynomial. Right? This is a very simple exercise that I sometimes put into master students in the classroom. And in fact, you can calculate the stationary points, and you can see that X star and X double star are global minimizers, of course, because if you plug them here, then you get exactly the matrix. And there is another stationary point, which in fact is a strict saddle, right? So this problem displays some symmetry, and of course, and in fact, many of these low rank matrix approximation problems display some sort of symmetry, which in fact helps a lot, right? So this is an example of a non-convex optimization problem, which is easy to solve in the sense that if you have an algorithm that can avoid these nasty strict saddle points, then every local minimizer is also a global minimizer. And in fact, this persists if you also go to higher dimensions, right? You will get a similar phenomenon for this particular problem. And this is not surprising because nobody would solve an optimization problem to compute the best low rank matrix approximation. What would you guys do? Who can tell me how you would approximate a matrix with a low rank matrix? Anybody? Linear algebra, what would you use?
Normally, we will use PCA, just do the eigenvalue decomposition and get the largest eigenvalue.
Exactly. So you would use the eigenvalue or the singular value decomposition if the matrix is non-symmetric, and you would keep only, the parts of the decomposition corresponding to the largest eigenvalues, right? To the largest one if you want a rank 1 or 2 and so on. So the simplest method for solving these problems without constraints that are smooth is, of course, gradient descent. Right? So gradient descent, very simply, you are at some iterate xk, and you compute the gradient, and then you take a step along the negative gradient, and if you select the step size small enough, then basically you are guaranteed to converge in some sense to a point, to a stationary point. Right. And in order to make things simpler here, we will assume that the function is L-smooth, as we call it, so it has Lipschitz gradient. So this is the condition that our function is to satisfy. And for functions that are twice smooth, this means that basically the eigenvalues of the Hessian are uniformly bounded by this constant L, which is we call the Lipschitz constant. Right. So we will analyze the gradient method, because it will provide the motivation for what will follow in this simple setting. And why the simple setting? Because basically this Lipschitz continuity of the gradient, this gives us this very important property, which is called the descent lemma. Basically, this tells me that I can bound the error between the function and the first order Taylor approximation of it, which is this one, by a quadratic function. Right, and in fact, this upper bound is valid globally, right? So at any point, and you see here how does this look like. So this blue function is a function that satisfies this L smoothness condition, and at any point I can draw a quadratic function. Notice that this is a quadratic function of y because I have my x fixed with a very simple Hessian, right? A Hessian a multiple of the identity. And then basically I guarantee that this quadratic function will be an upper bound globally to my function. And this holds for any point, right? And of course, then, it's basically gradient method boils down pretty much to minimizing this quadratic upper bound. So it is easy to minimize quadratic functions. And this is an upper bound of my function. So what if I minimize this in order to get the new iterate, and this is what gradient descent does basically. So it uses a quadratic model, right? with a very simple Hessian approximation. So this is first order Taylor expansion, and it says because the second derivatives might not exist or because I don't want to compute them, I will use a very dumb, let's say, diagonal approximation of the Hessian. And then I will minimize this because it's a quadratic function and I know how to minimize this. How can I minimize this? I set the derivative to 0. By the way, is this a convex function or a non-convex function as a function of x? I didn't ask you if you know things about convexity. I guess you all know, right? So this is a strongly convex quadratic function because its Hessian is positive definite. This gamma here is positive, right? And to minimize this, I take the derivative with respect to x, right? And basically, if I do this, then I get this guy. This is the first order condition for optimality, which is both necessary and sufficient because we have a convex problem, a quadratic problem. And now if I solve this for s, call this xk plus 1, I get the gradient step. Right. So one way of viewing gradient descent is as a majorization minimization procedure. So first, I have at my disposal an upper bound on my function, which is simple enough and I can minimize. So this is sometimes called a majorizer. And then, because it is simple to minimize, I will minimize the majorizer, and the minimizer of this upper bound will be the new iterate, right? And in fact, very easily I can show convergence, right? So suppose that gamma is smaller than 1 over L, then basically this is indeed a majorizer. And so then I have that, you know, by the property that I showed you before, by this descent lemma, I will have that the cost at the new iterate, of course, because this descent lemma, because of this descent lemma will be smaller than the quadratic approximation. And this quadratic approximation, basically it is, you know, simply I put here the gradient step, and I obtain that this guy is equal to that guy. So you see that immediately what I get is that I have descent, right? So the cost at my next iterate is smaller than the cost at my current iterate, minus some quantity which only vanishes once I have landed at a stationary point. So in other words, you can view the cost as a Lyapunov function, right? For those of you, most of you, I guess you know control and Lyapunov stability theory. We have a dynamical system here, right? You can view this as a dynamical system. And we want to show that, you know, some equilibrium point is stable. Of course, the equilibrium points here are what? By equilibrium points, I mean whenever the right-hand side is equal to the left-hand side. So whenever I end up at a fixed point. And of course, equilibrium points here are, you know, the points where the gradient vanishes. And, you know, in order to prove this in dynamical systems theory, we are looking for some Lyapunov function, a function which decreases along the trajectories of the dynamical system, and so on, and it is bounded below, and so on, right? And in fact, you know, then we can show convergence because we can use a very simple telescoping argument, and this is in all the proofs that that underline these algorithms that we are doing. So suppose you are using some constant step size. So you write this for consecutive steps, and then you sum up. And if you do this, you know, these guys vanish, and what is left? Only the first and the last term. Right, so you can write this down as you get something like that along the trajectories, right? So now basically, if you transfer this on the other side, and you let k go to infinity, you will show that the sum of all the gradients norm square is finite. And when do I have an infinite sum being finite, which is an infinite sum of non-negative terms being finite? Whenever, of course, the sequence of these terms goes to 0. So this shows that the gradient vanishes if I let the gradient descent run for a large number of steps. Right. So this is a very easy proof, which is, however, very common in algorithms which are more complicated than gradient descent. Right. And the cost here plays the role of a Lyapunov function. And here, you know, I have a graph where it illustrates this. So you are at the current iterate, and then you form this quadratic approximation with upper bounds, and this is the minimizer. And you see that, you know, you go closer and closer to a local minimizer. In that case, it happens to be global one. But of course, if you start from the other side, close to this local minimizer, then you will end up there. So, of course, gradient descent can converge to local minimizers. However, people have recently rediscovered, let's say, that that it avoids strict saddle points almost always. And by this, I mean that if it's started, if it is initialized randomly, right, then basically it will converge to a point which is not a strict saddle in the sense, what are strict saddles? Again, points that are stationary, the gradient vanishes, and that they have a strictly negative eigenvalue of the Hessian, right? And there is this very simple example that can illustrate this. So you have again some fourth degree polynomial here of two variables. The function looks like that. It has two global minimizers over here, and it has a strict saddle at the origin, right? So these are the level sets of the function. Now, if I start my gradient descent from any point which has a second coordinate equal to 0, and the first one is something different, then basically, indeed, it will converge to the strict saddle, right? And here, you know, you can see the gradient flow of gradient descent here. Right? So gradient descent, you can view this as an Euler discretization of this differential equation, right? So here you see here that these arrows, if they start on this line, they lead to the saddle point, to the strict saddle point. If you slightly perturb the second coordinate though, so it's not exactly this 0, then you will see here that they start diverging and converging either to one global minimizer or to the other, depending on which minimizer they are closer, right? So gradient descent for smooth unconstrained optimization almost always avoids strict saddles in the sense that the set of initial conditions for which a method will converge to a strict saddle point is of measure 0, right? And this is somehow a reassuring result, right, for these simple methods that even though they don't use second order information, it is very unlikely that they will get trapped into one of these nasty saddle points, right? We will see later that, you know, things like that, when you have non-smooth terms, things become more complicated. So we cannot state something as simple as that. We will need some other conditions to be able to state that projected gradient or proximal gradient method avoids saddle points. So, and here is a summary of what you can say about the gradient descent method, right? In this simple setup of null smooth function, where basically you have constant step size, gamma equal to 1 over the ellipsis constant. Why somebody would choose this step size? Because it is the one which gives you the largest descent based on this theoretical bound on the descent lemma, right? So, of course, this requires you knowledge of the ellipsis constant, which is not, most of the cases, this is not happening. So you need to do some line search anyway, but for theoretical purposes, people tend to analyze this for constant step size, just to see the order of convergence, which is slow, right? I mean, it is indeed slow. For general non-convex functions, we get a sublinear rate on the minimum of the square norms of the gradients, and this is the best that we can say, right? So this is rate 1 over k. So this is called sublinear. In the convex case, and what does convexity give us extra? It gives us that, you know, not only do we have this uniform upper bound around every point, but we also have a linear lower bound that passes through this point. Or in other words, we have a hyperplane supporting, let's say, the epigraph of the function, right? And this gives us some extra inequality that allows us to derive a sublinear convergence rate in terms of the function values, right? And of course, here this f star is the global minimum cost, right? Because of course, any local minimum is also global for convex functions. But again, the convergence rate is sublinear, right? Again, under these assumptions that we put, right? That's the best that you can hope for. And in fact, there exist functions for which gradient descent will attain exactly this rate. Not exactly, because this is not the tightest version. There are tighter versions that only differ in the constant. Now, when we move to the strongly convex case, or when I have not only a quadratic upper bound, but also a quadratic lower bound, which is positive definite, then basically I can show that I obtain linear convergence. So this is called linear convergence rate, or Q-linear rate, in fact, because we have that at every iteration, the error term strictly decreases by a margin, right? Contracts, in fact. And this is the contraction rate or factor, as it is called. And mu here is you can view this mu as the smallest eigenvalue of the Hessian. And this will be non-negative, right? Because now we are dealing with strongly convex functions. In fact, because this function is not linear, this is the minimum of the minimum eigenvalues. And L will be the maximum over all x of the maximum eigenvalues of the Hessians. Right? And you see here that the convergence rate becomes slower whenever L is much larger than mu. Right? Whenever the function is ill-conditioned, then this bound tells us that the function, that gradient descent might converge very slowly. Why? Because this guy here will become very small. So 1 minus something very small is very close to 1. And raising a number close to 1, to some power, it doesn't do much, right? You need to wait a lot. So if this is 0.9999, then we are in trouble here. Gradient descent will be very slow. And in fact, you can see this with a simple 2D example, right? You don't need to construct complicated examples to see that the gradient descent can be slow. So here we have a quadratic function of two independent, I mean, there is no coupling here, basically, so you could minimize. So what is the minimizer here, by the way? Who can tell me to see if...
0.
0, right. So it is very easy to compute. It is a 0 vector. This is a strongly convex function, a quadratic with positive definite Hessian. The Hessian is basically a diagonal matrix. This is kappa here, right? So we assume that kappa is larger than 1. So, you know, L is equal to kappa and nu is equal to 1. And basically we call this kappa the condition number, which was, you know, it is the same that people use in linear algebra for a condition number. Right. So now if I apply gradient descent here, I can very easily write down the equations of the update. We see that the method converges whenever gamma is small enough. In fact, 2 over the ellipsis constant. So even though before we saw this majorization, minimization interpretation, when gamma is smaller than 1 over the ellipsis constant, it is well known that gradient descent converges when the step size goes up to 2 over the ellipsis constant. But if it goes outside, then we don't have convergence. And in fact, for this example, you can verify this. Now, whatever gamma I select within this range, then I will converge to the unique minimizer with a linear rate, but it will be very slow, right? Because the rate, you know, if I take gamma 1 over the ellipsis constant and I start from 1, 1, then basically I will immediately make the second coordinate 0, I'm good, but the first one will go to 0 very slowly, right? So I might need, you know, more than 1 million variables to obtain a good approximation of a minimum more than 1 million iterations in order to obtain a good approximation of the solution. Right. Of course, Newton's method, you know, it is much better because it uses a much better model. It uses a quadratic model, where now instead of a silly approximation of the Hessian, a diagonal, it uses a true Hessian. And in fact, for this problem, will converge in 1 iteration. Nevertheless, it might diverge, as Moritz told you, if it is not started close enough to a local minimum. And even, you know, even for strongly convex functions, this function is strongly convex. In fact, you know, if it started slightly off, then it will diverge. So you need somehow to ensure that the method converges, and the way to do this is through line search. Right? Again, we have the step size here. And now we want to guarantee, in order to be able to show that f is a Lyapunov function, we want to guarantee decrease. So we want to choose a step size so that the cost decreases, right? And we can do this because we have assumed smoothness. So if I take a first order Taylor expansion, then I have this remainder term here, which goes to 0 faster than what gamma goes to 0. And this means that because this guy is negative, right, this is a descent direction, provided that the Hessian is positive definite. Then for gamma small enough, I will be able to satisfy this inequality, and I will be able to show some sort of convergence. Now, quasi-Newton methods can be applied in case you don't want to compute the Hessian, or whenever your function is not twice smooth, or whenever, you know, you have a large problem, and in fact, then there exists limited memory quasi-Newton methods that, in my experience at least, they are very, very efficient. Again, now you minimize a quadratic model, but now you pick as a Hessian a different matrix than the Hessian of your true function. And you want this Hessian to satisfy certain properties, right? If you remember before, Moritz, you know, drew this figure that, you know, Newton's method is basically, suppose that you solve a nonlinear, you want to find the root of a nonlinear equation, because this is what all these methods try to do. So basically you are at some point, you linearize around this point, and you solve the linearized equation, and you obtain the next iterate, right, until you converge to the root. Now, in quasi-Newton methods, which are a multidimensional extension of the second method, basically you take the last 2 iterates, and you draw the line that passes through them. So it's like, you know, you basically, you are approximating the derivative with a finite difference. Right? In one dimension. In multiple dimensions, there are many ways to do so, of course, right? But, and for each one of them, you obtain a different Cauchy-Newton method. But the main idea is the same, that you want to satisfy this secant equation. Of course, now you don't divide with scalars, but you want to satisfy this secant equation, right? So yk minus 1, which is basically yeah, that's something that I write here. It is a difference of the two past gradients, and sk minus 1, it is the difference of the two past iterates. So you want your matrix to satisfy this system of equations, right? Of course, this is a system of linear equations, and in fact, you have more unknowns than equations. So there is, you know, there are more than one ways of satisfying the second equation, and each one gives different Cauchy-Newton method. The most efficient being, after all these years that people have been studying this, perhaps the most efficient being BFGS, as it is called, and for which there exists a limited memory variant, which is called limited memory BFGS. And why is this nice? Because it uses the same information as gradient descent, just a gradient. And in fact, it only uses vector-vector products to compute on the fly the minimizer, let's say, of this quadratic model, which is, you know, basically on the fly, it computes this quantity by very simple operations. So there is no need to form a big matrix. There is no need to invert a matrix. You just need to carry out this two-loop recursion, as it is called, in order to calculate the matrix vector product with a gradient, right? So even though the computational cost per iteration is comparable to the gradient method, in practice, usually you get much faster convergence. Okay, now I think we can, shall we have a short break or shall we continue?
It's up to your plan. I found that you still have plenty slides.
Exactly. So I have a lot of slides, so I think it's better to continue.
Yeah, we can continue. And then if anyone have questions, I suggest them to interrupt you directly to pose the question.
Yes, feel free to interrupt me if you have any questions. So, okay, now this was for smooth problems. What about non-smooth problems? For non-smooth problems, and especially non-smooth non-convex problems, things become quite complicated. And of course, now let's talk about this problem. This can be quite general, right? This can be anything. The only assumption that I put is that the function is proper, meaning that you know, there exists a point which for which this function achieves takes value smaller than plus infinity, and so on. So here with this R bar here, it is the what we call the extended real line, right? So it is the real line taking the union with the plus infinity. So, you know, these are very weak assumptions on the function, and you can model constraint problems and everything, right? So, of course, it's not easy to find, you know, a simple quadratic model like the one we showed before for this type of problem, right? One conceptual method for dealing with this problem. So, you know, your function might look like this. So this is a point of non-differentiability, and you see here that the function becomes equal to plus infinity outside some outside of its domain, right? So this is what we call by these extended real-valued functions. And typically, you know, you obtain such a function when you have a problem with constraints. So the proximal point algorithm does something very simple. Again, it is based on this majorization minimization principle. Basically, now it follows a very, again, silly model in the sense that it doesn't change the function at all. It doesn't simplify it like we did before with the gradient method where we're taking a first order Taylor expansion. It just adds a regularization term which penalizes deviations from the previous iterate. And there are several reasons that you want to do this, right? First of all, you are adding a strongly convex term to a non-convex function. And if your function is not that non-convex, if it is what is called hypoconvex, then basically by choosing gamma small enough, by making this regularization stronger and stronger, then the sum will become a convex function, and then you can minimize it easily. So you can solve a non-convex problem by solving a sequence of convex problems, right? This is one of the applications of proximal point algorithm, right? And again, it follows the same principle. Of course, this model function here, it is an upper bound. If I'm able to minimize it, it doesn't seem very well on the slide, then I end up somewhere here. So you see that I'm approaching the minimizer. So it is again a majorization minimization procedure, and I can very easily show convergence, right? And in fact, I can write this proximal point iteration, which is again a conceptual algorithm in the sense that sometimes this problem is as hard to solve as the original problem, right? You can write this iteration as xk plus 1 being a proximal point of phi at xk. So by proximal point, I mean, you know, the minimizer of this regularized version of phi that I showed you before. And you can show that being a fixed point of this guy is a necessary condition for optimality. So x star is a local minimum. If x star is a local minimum, then the proximal point iteration basically stops at such a point, right? So it doesn't do much. I will skip this. Yeah, so a relationship between the two. So we had before, you know, if your function is smooth, we were taking a gradient step. In fact, the proximal point step can be seen as an implicit gradient step. So suppose for simplicity that this function is smooth here, and I want to, you know, in order to compute the proximal point, I minimize this function. So the optimality condition, you know, I take the derivative and set it to 0. So suppose that x bar is the proximal point. So it looks, I mean, suspiciously similar to what we had before. However, now x bar, the next iterate, you know, is a gradient step which involves the gradient at x bar itself. So it is an implicit gradient step. Another way to view this is that we discretize, you know, the gradient flow. In gradient descent, we use an explicit Euler method. In proximal point algorithm, we use an implicit Euler method to discretize it, right? And usually implicit methods, I guess Moritz told you, they are behaving better, especially if you have, you know, nasty problems. And of course, another special case is whenever your function is the indicator of a set, then the prox becomes a Euclidean projection. Right? And another object that we can attach to this proximal mapping is now by looking at the value function of this optimization problem. And this is called the Moreau envelope. Right? And by doing this, basically, we construct a function which is now real valued. So even though my original non-convex function might take the value plus infinity, the Moreau envelope, which in this figure I show the construction, at some point x, basically I build this quadratic, this nonlinear model of my function, this regularized model of my function. I minimize it. This is a minimizer. So this is the value of my Moreau envelope at this point x. Right. So it is always real valued. And you can see from the figure that it is also, if you do this for all of the points, then you get a function which is a lower bound on the true cost. Right. It is a lower bound on the true cost. And it is also a continuous function. Right. So this is nice because we have converted, a nasty problem with a problem of minimizing a function which is continuous. And you see here that, in fact, this function preserves the minimizers. So the minimizers of the Moreau envelope are, in fact, the minimizers of the original nasty function. Right? And, in fact, for some classes of functions phi, the Moreau envelope can also be made smooth by choosing gamma small enough. In fact, for convex functions, the Moreau envelope is always a smooth function. Right? So it is real valued continuous. The two problems are somehow equivalent. And, even for these nasty functions. And basically, proximal point method can be seen as a gradient descent on the envelope function, on the Moreau envelope function. Why? Because, whenever phi gamma is, whenever phi is basically hypoconvex, and by hypoconvex I mean it is a function, so a function is called hypoconvex if I can add to it a quadratic term and make it convex. Right. So, for instance, this function here, this blue function here is a hypoconvex function, right? So now we see another interpretation of the proximal point method as a gradient descent, something which we very well know, on some surrogate function, which is the Moreau envelope. But of course, as I told you, this is a conceptual method because most of the times I cannot really solve this problem. But typically, proximal point algorithm, as I told you, it is used as a way of convexifying problems. And this is one application of proximal point algorithm in an algorithm for solving non-convex quadratic programs, an algorithm which we call QPAL. So basically here you have a quadratic program, and you have seen that QPs are usually very frequently met in sequential quadratic programming, so where you basically form a quadratic approximation of your problem. And typically there, you are not sure that the Hessian of the Lagrangian, because this is what you use as a Hessian approximation in your sequential quadratic program, will be positive definite. So it can as well be indefinite. So it is not very uncommon to have non-convex QPs. So what you can do basically is you can apply the proximal point algorithm that I told you before, right? So you defined this as your abstract cost, let's say. It is exactly as this problem. So I add with this the indicator of the box evaluated at AX. And then I apply this proximal point iteration with some, more elaborate choice of this weight. I mean, instead of having just a scalar, I can scale each coordinate. And now here I have a convex problem at each iteration. And of course, there are many ways of solving this convex problem. In that case, in QPalm, we basically again apply proximal point algorithm, but to the dual of this problem, which is equivalent to the augmented Lagrangian method, right? So it boils down to minimizing at every step this function here. This is the square distance. It is basically the Moreau envelope. So of the indicator, right? So this is the Moreau envelope of the indicator. Now I don't have a gamma here. I have, you know, a diagonal matrix. So now this function here is smooth. In fact, it is a piecewise quadratic function. So I can minimize it very efficiently using Newton. In fact, I can also do an exact line search. So I can very quickly minimize this function. And in fact, because here I have a QP, I can solve linear systems easily because I can update the factorizations. The matrices do not change. And in fact, in this QPalm method, at every iteration, what happens is that you obtain a linear system in order to compute the Newton direction, where basically some rows and some columns are added to the matrix, or they are deleted from the matrix, and you can do this using low rank updates. So this is an application, let's say, of the proximal point algorithm, and you can show that the iterates generated by this algorithm converge linearly to a point satisfying the KKT conditions, and you can make the linear rate as high as possible, you know, by choosing the penalty parameters high enough. And these are some comparisons, right? So this is a very, let's say, hard collection of problems, these Maros-Mezaros QP problems. And here we compare QPalm with OSQP, which is basically an operator splitting method for solving QPs based on Douglas-Rafford splitting, and against Gurobi, which is an interior point method. And you know, this is some metric of related to the runtime. So the smaller, the better. And this is the failure rate, because I told you some of these problems are so tough that many solvers cannot solve them. And these are some performance plots. So the algorithm, I mean, QPalm has a balance between being reliable in the sense that it can solve most of the problems. And this is thanks to the Newton type iteration that we do for the subproblems, right? And the efficient updates. And it is also quite fast, right? And some other examples here. So it is not always the best choice. So this is for linear MPC. So here you can see that, you know, QPalm is the blue one. Gurobi here, it is faster. But if you do warm starting, this figure, you know, corresponds to solving a sequence of optimal control problems where you warm start. OSQP and QPalm and QP Oasis as well, they can benefit greatly from warm start. Gurobi, which is an interior point solver, not that much. Right. So this was just an application of, and these are for non-convex QPs. So I will not go into detail. So you can find this solver by clicking on this link. I will send you the slides. Now let's move on to some more, let's say, problems that have more structure. So in general, problems do not typically, nobody gives you a function phi, which can be anything, and tells you to minimize it. One structure that is very common is when phi is basically the sum of two terms, or you can write it down as the sum of two terms, where one of them is smooth and the other is non-convex, but easy to prox, in the sense that I can compute the proximal operator of this G in closed form. And there are many such functions and many constraints. For instance, you know, if you have cones or manifolds like the Stiefel manifold, or box constraints, or so on, then the indicators of all these sets are proximable functions in the sense that you can very easily compute its proximal operator. And also many non-smooth regularizers that I showed you before, like the nuclear norm and so on. Right, so now the idea here is that since I decompose my function into two parts, and one of them is smooth, then I will do a gradient step on the smooth function and a proc step on the non-smooth function. And this is, that's how this is an example of a splitting method in the sense that it splits your problem into two parts, and there's something simple to each one of the two parts. And the other way of viewing this basically is by using this quadratic upper bound on the smooth part and not touching the non-smooth part, right? By completing the squares here, I can write this term here as such. This is just a constant, so when I minimize it, it doesn't. When I minimize this function, it doesn't matter in terms of the minimizer. So you can also this term. So you can very easily see that, if I minimize this guy plus this guy, then this is the prox of G at the gradient step. So that's why it is also called forward-backward method, because I take a forward step and then I take a backward step with respect to G, right? And this somehow generalizes gradient descent. Of course, if you take G equal to 0, then the prox of the 0 function is basically the function itself, the unit, the identity matrix, right? If you take as G the indicator of a set, then you obtain the projected gradient method, and if you take f equal to 0, then you obtain the proximal point algorithm. And again, through this majorization minimization principle, we can very easily show descent, right? So again, the algorithm converges using again the same idea. But as I told you before, as you showed, gradient descent is very slow, right? So this is like an extension of gradient descent to this structural problems, f plus g. So the question is how we can have Newton-type versions of this proximal gradient method. And the first attempt is what people typically do in sequential quadratic or sequential convex programming method. So you use a more accurate model, let's say, for the smooth part. So you would use here the Hessian. Suppose that you can compute the Hessian of f, and then you would minimize this model. But now you cannot get a closed form solution like before when you didn't have this non-smooth term, right? So now basically you need another solver to solve this problem, and that's something that we want to avoid because we want simple algorithms that scale well with problem dimension. So this is something that has been suggested in the literature, but we will not follow this approach. We will show something different. The second attempt basically is to, somebody would think of, okay, you told me that this proximal gradient generalizes gradient method. So what if instead of a gradient step here, I take a Newton step, right, with respect to the smooth part, and then I take the prox. This algorithm doesn't do what you want it to do. It's fixed points, so when it stops, it might stop to points that do not correspond to local minima of your original problem or anything related to it. So this doesn't work for an arbitrary matrix H, right? So the view that we follow here is basically that we view this problem as a root finding problem, because all these Newton type methods basically they try to find roots of nonlinear equations or solutions of systems of nonlinear equations. So basically the optimality condition is that, and the algorithm would stop whenever x is equal to the forward-backward step of itself, right? In other words, if I'm able to solve this nonlinear system, X will satisfy the necessary condition for optimality, right? Which tells me that if X star is a local minimum, then basically X solves this nonlinear system. In fact, for some very non-convex functions, the prox will not be a single valued mapping, right? So because the problem might have more than one minimizers here. So that's why here we have an inclusion. But for all functions that you can think of, at least locally, close to X star, this mapping here will be single valued. And then you can apply, the traditional Newton type schemes for solving nonlinear equations. Right? So this can be the inverse Jacobian of the forward-backward residual, as we call it, or some limited memory Quasi-Newton approximation of it, and so on. Right. But of course, now the question is, how you can guarantee convergence, because by doing this iteration, as we said, even in the unconstrained smooth case, you might not get convergence. But then we were doing a line search on the smooth cost. But here things become even more complicated because, in fact, this point might not even be feasible, right? So it might be outside of the domain of the cost function. So you cannot really rely on the cost function to show descent, right? So what is the solution? The solution is to rely on something which looks like the Moreau envelope, but for this composite problem. And again, the idea is exactly the same as in the Moreau envelope. So now we are looking at the value function of this sub-problem that we solve at every iteration. And this defines another function, which we call the forward-backward envelope. And it has also very nice properties as the Moreau envelope. But the nice thing now is here that we can easily evaluate this function, right? Once we are able to carry out this step, and then basically we also have the value of this function by plugging this point here, which is the minimizer of this function, right? And again, minimizing the original function f plus g, it is the same as minimizing this function, the forward-backward envelope, which is real valued and continuous, right? And here is the forward-backward envelope of this non-smooth function, a non-convex function. And the nice thing here is that if I carry out one step of the proximal gradient method, then this step will also decrease the forward-backward envelope. So not only the cost itself, but also the forward-backward envelope, right? And this is a key because this will allow us to do some line search on this. And in fact, you can, whenever this envelope function is smooth, and it is smooth whenever f is twice smooth and g is hypoconvex, then again, proximal gradient method can be seen as a scaled gradient descent method on this forward-backward envelope. Right. So now the idea, in order to inject, let's say, Newton-type steps using the idea that I showed you before, is basically to do a line search on the envelope function. But because the envelope function might not be differentiable, we are doing a peculiar type of line search here. So we are forming the convex combination of 2 points. X bar here is this nominal update, as we call, for which we know that we have guaranteed descent. Right, we have guaranteed descent given by this formula here. And now, because my function is continuous, the envelope function is continuous. This means that if I slightly perturb this x bar hat, xk bar, then I will still get descent, right? This means that I can take some Newton type step here, and I can form the convex combination with a nominal step, and then I'm guaranteed that for small enough tau, so moving away from this step, eventually I will be able to get a point which decreases the forward-backward envelope, right? Of course, in that case, this D can be anything here. It can be even noise. So this is a property. This is like continuity properties of Lyapunov functions leading to some form of input to state stability, I think, right? But of course, here we would like this direction to be good enough to be a Newton type direction. And we would like, in fact, when we are close to the solution, the step size to become 1, so that the method becomes equivalent to the pure root finding Newton type method, which has very good convergence properties like superlinear or even quadratic convergence. And in fact, you can show that indeed this merit function here, as it is called, will allow unit step size to be accepted, and you will obtain superlinear convergence, right? Provided that the direction here is truly, let's say, Newton type. So either it involves a Jacobian of the forward-backward residual, or some full matrix quasi-Newton approximation of it, right? So this is a simple way which involves only linear algebra of designing a superlinearly and globally convergent algorithm for non-smooth, non-convex problems that have this structure of F plus G, right? F smooth plus G non-smooth, but easy to prox. This is one example of how the line search works. I will not go into detail. I mean, you can very easily see in the figure. And yeah, this is what I told you. And the same idea basically can be applied to any problem for which you have a function which is continuous. It doesn't even need to be smooth, and you have some point that makes this function decrease sufficiently. Then you can do this line search trick basically to get to combine the algorithm with some other directions that are converging rapidly when the start are close enough, but you don't know what they will do when you are far enough from the solution. So you want some line search to guarantee descent, and you don't have a smoothness in your problem. Some experiments here, and indeed, even with limited memory BFGS, because this is what we usually use in PANOC, because it is if you use limited memory BFGS, basically you don't need any extra information from your functions compared to what proximal gradient needs, right? You just need to be able to compute the gradient of the smooth function and the prox of the non-smooth function, and that's all. And then if you can apply proximal gradient, then you can also apply PANOC, right? So that's why we use LBFGS, because it is somehow, blind to any other problem structure that would require some extra information from the user. And here is how the algorithm performs in some convex examples. First here, because when we were doing this, we were comparing against also the fast proximal gradient method, or FISTA. And indeed here you see that these Newton type steps, they help a lot. And at the same time, you also get global convergence, right? Global convergence meaning that if I start the algorithm from wherever I started, I'm guaranteed to converge at least to a stationary point. It will not diverge. Right, and here's a non-convex problem, this dictionary learning, right? And of course, one prime application of this algorithm is also solving optimal control problems when you control systems using model predictive control. And we have also tried this out in some real-life experiments. Where we try to avoid some obstacles. We have some trailer, and the goal is to reach at the destination while avoiding the obstacles. Of course, then the problem becomes very non-convex, right? Because obstacles, I mean, whatever obstacle you have, even if it is convex, the problem is non-convex. Anyway, so we use this PANOC algorithm in conjunction with a quadratic penalty method. Of course, Panos is only able to deal with simple constraints like box constraints. But if you use it as an inner solver to some other method, like quadratic penalty method or the Lagrangian method, then you get a fully fledged, let's say, solver for solving nonlinear optimal control problems, right? And if you, play with the parameters a bit and you have a good way of selecting the tuning parameters of these outer methods, then in fact the algorithm performs really well and is able to solve very quickly this type of problems, right? Some comparison here with some state-of-the-art solvers, IP-opt, and so on. Right, and this is, a very simple algorithm in the sense that the only thing that it does is that it does proximal gradient steps, and in fact, in that case, it's projected gradient. So it means I take a gradient of the cost, and then I project on the box, right? I check each one of the coordinates of the gradient step, and if it's outside of the box, then I put it back in the box. That's what I'm doing. Plus some limited memory BFGS, which is just vector-vector products, right? And, you can achieve some quite some speed here and we have tried it in drones in collaboration with people from Sweden, and it works as expected. And there is software that I highlight at the end. Okay, now I think because it's getting a bit too heavy, I will stop here to take some questions and have a short break for 5 minutes, and we will continue later, quickly going through Bergman proximal algorithms and Douglas Rafford splitting and Admm. So if you have any questions.
Yeah, actually, I have questions regarding your algorithm. At the beginning, you start to introduce all the idea with majorization, minimization. But actually, later when you mention the moral envelopes, it becomes it's no longer majorization. It's a lower estimate of the original functions. Is there any link between these two ideas? I only noticed that the stationary point for the majorizer and the lower estimate are both fixed points. But why does the proximal sometimes works better than using the gradient with the majorization?
Okay, first of all, yeah, so now you are asking, so suppose that you have a function which is L-smooth, should I use the gradient descent or the proximal point algorithm, right? Because both of them, they use a majorizing model that you minimize and you improve. This is what you are asking, or am I missing something?
It's correct. Yeah, I mean, what's the link between, because at the beginning you introduce all the thing with majorization, right, but right. After that you use FBE, it's a lower estimate of the original function. Is there any link?
The link is that, I mean, if you want this to be a lower bound of the Turcos function, you need the guy that you are minimizing here to be a majorizer. So yes. Only then you get that this function is a lower bound, and you have minimizers that agree with the minimizers of the original function, and so on. So it is really crucial that you have a majorizing model in order to define this forward-backward envelope, right? So that's a link. So it is very important. I mean, maybe it's not highlighted because you need to see the proofs for that, but then you will see that indeed you need this majorization property in order to be able to show this equivalence here, that minimizing phi, which is the ugly function, is equivalent to minimizing phi gamma, which is the nice function.
Yeah, I understand now. Thank you.
Other questions? Okay, so then let's continue. I mean, quickly, I will talk about an extension of these algorithms. Well, basically the idea is quite simple but far-reaching. So basically you replace the Euclidean distance that we were seeing everywhere with something else, which is called the Bergman distance, right? So here, this is the proximal gradient method. Here you have this quadratic term, and you want this because you want this guy to be a majorizer, as I told you, because then you can show convergence, right? So the standing assumption here is that you have this quadratic upper bound. And then for gamma small enough, smaller than 1 over L, you have this majorization minimization property. So you can show convergence. But of course, not all functions, basically, and this is implied by ellipsis continuity of the gradient, right? Right, which is, implied by the Hessian having uniformly bounded eigenvalues. But of course, it's not always, I mean, most of the functions do not satisfy this property, right? Then what can you cannot apply this method. You can apply it by doing a line search on gamma, right? Basically decreasing it, until you have a property like this being satisfied locally, because, for any function which is twice continuously differentiable, locally, the function satisfies a property ellipsis continuity of the gradient, but this constant is not uniform over all x and y, right? So you need to adapt gamma at every iteration, or otherwise, you can choose a different metric here, and then you are expanding the functions, right? So, and another property that implies this descent lemma is basically if this function is convex here, so L over 2 square norm of x minus f of x, then basically you can show, if this function is convex, that this inequality is satisfied. Why? You apply convexity of this function. Let me call this h. So convexity gives us this linear under approximation. So now if you replace wherever you have h, you replace this guy here, you will obtain this inequality. So people recently, I mean, starting, there were some recent papers around 2015, I think, by Bauske, Bull and Bolt, and one in parallel by Nesterov and co-workers, where they said, okay, let us replace this guy here with some other distance between the 2 points, where this distance is induced by some function h, so-called distance generating function, right? And then, of course, I can expand the class of problems for which proximal gradient type of algorithms can be applied, because as I told you now, this is quite restrictive, right? And in fact, basically this tells you that your function shouldn't grow at a rate which is higher than the rate that the quadratic increases. So you should be able to sandwich your function between two quadratics, right? One convex and one concave, right? Because you have a similar inequality in the lower bound. So basically polynomials of higher order, even though they might be convex, or x to the power of 4, of course they don't have a global ellipsis gradient. But what they have is that they are relatively smooth in the sense that they satisfy an upper bound like this for some Bergman distance. So what is a Bergman distance here? It is basically you are given a function h, and then you see what is the error of the linear approximation of h. Again, all these linear approximations, they come very often into the picture, right? And you know that if h is strictly convex, then basically this is larger than 0 if x is different than y, right? So that's why it is somehow like a distance. Of course, it is not symmetric, but it has a behavior similar to a distance. And in fact, you know, it has, I mean, for different h, you can obtain different Bergman distances that people use to measure, for instance, distances between distributions in infinite dimensional space and so on. But bottom line is that you can basically, in fact, show that proximal gradient method is in fact equivalent to Bergman proximal point algorithm by defining this distance generating function, right? So you can write the proximal gradient method as a proximal point algorithm, but with a metric, let's say, which is different than the Euclidean. And it needs, of course, the function f itself. So if you expand this guy using this formula, then you will obtain exactly this guy, right? So this is just an observation which, you know, shows that Bergman proximal point algorithm is general enough because, you know, it contains, of course, the proximal point algorithm and proximal gradient descent or forward backward splitting. And in fact, in that case, for this Bergman distance, the Bergman Moreau envelope, let's say, becomes basically the forward backward envelope, right? And of course, you know, you can apply now a similar idea to problems that are more complicated, that have constraints, because these Bergman distances, some of them, they act as barriers, keeping you inside the feasible set. Right? For instance, take the KL, the Kullback-Leibler divergence. And you can also relax the condition that I showed you, this L smoothness to relative smoothness, which was this, let's say, breakthrough result by these authors, which was later found that there were some people in 2010 that had already suggested this. So f is relatively smooth whenever, you know, these functions are convex. Before, in the Euclidean setting, I told you that, you know, this function, if this function is convex, then the descent lemma is satisfied. Now, basically, if this function is convex, then you have a descent lemma, but with a nonlinear term different than the quadratic, right? And then you can minimize it, right? And you can leave G unchanged. And then you can come up with a Bergman proximal gradient algorithm, which is, however, and that's something that people might not have observed, this is no more general than, again, the Bergman proximal point algorithm, because you can choose a special distance generating function and you can write this guy as a proximal point algorithm with this Bergman distance, right? And of course, you know, you can then apply an algorithm similar to Panos to solve problems where basically you have more complicated structures, and this is summarized here. So for instance, again, if you have all these problems that involve a term which has some low rank approximation meaning, right? We showed before this type of structure. So this is a polynomial of degree 4. So of course it doesn't satisfy the Lipschitz smoothness assumption. However, it is relatively smooth to a kernel, to a distance generating function of this form. Let me keep this now in the scalar setting so I don't complicate you with variables. So if you take this example, then you can find basically a Lipschitz constant, a relative, let's say, Lipschitz constant, so that this function will be convex, which will depend only on the problem data, right? So then you can use a constant step size, right? Because you have this majorizing property uniformly now, even though your function is a polynomial of degree higher than 2. And you can get all these nice properties, and then this means that you can also do this Panos take by using the Bergman forward-backward envelope and so on. Now I will, in 5 minutes, I will talk about finite sum problems, which are large-scale problems that people typically encounter in machine learning applications, but also in distributed optimization, right? You can view this as, you know, you have a problem here where you have many players, each one has its own cost, and they try to collectively minimize a common cost, and you also have some regularizer here or some constraint. Right, so basically what you can do is that you can formulate this as a wait. Yes, you can introduce this consensus formulation, and this is a very common take in these problems. So basically you can write the problem as right, so you can write it as such. And now typically if you want to get, you know, computations that lead to distributed implementations and so on, you apply block coordinate descent. By the way, here, you know, suppose, let's forget this term for a minute. You know, when you train a neural network, you end up with a problem like this. People typically apply stochastic gradient descent. So the next iteration would be, in the extreme case, you know, you would only keep move along the gradient of one of these guys, right? So this is stochastic gradient. And because this can be viewed as an inexact gradient method, basically you cannot use a constant step size. You need to use a step size that goes to 0, right? In order to somehow get rid of the noise asymptotically. And then people, you know, they came up with this type of algorithms where basically the only, so now the main advantage here is that you don't need to go through all the data. Suppose that this n here is huge. At every step, you only need to compute the gradient of one data point or of one of these functions. But the method is slower, right? Because it is stochastic gradient. So it is slow, and partly because, you know, the step size goes to 0. So recently people came up with these algorithms where basically, again, you compute only one gradient per step, but by combining it with some other terms that you keep in memory, you end up with an algorithm which doesn't need a diminishing step size. And in reality, you know, this means that it will converge faster. You know, for strongly convex problems, you will get linear convergence rates under certain conditions. and by only evaluating only one term of the sum, right, at every iteration. And these algorithms, you know, there are, I mean, SAG, SAGA, SVRG, and so on. Finito. And, you know, they are a bit weird because the analysis is a bit complicated. And so they don't have a common Lyapunov function. So here, basically, we show that one of them, this finito algorithm, is basically block coordinate descent applied to this formulation. But because block coordinate descent, usually you want your constraint set to be separable. Here we need a different analysis, and the analysis that, I mean, you can show convergence by using the forward-backward envelope again. And then you end up with what is called finito miso, and it's Bergman version, for instance, for fully non-convex non-smooth problems. And you can also come up with, you know, Newton type and limited memory BFGS versions. So this is the vanilla version, but perhaps I should show you the. Yeah, so here you can see that this yellow one is finito with line search and limited memory BFGS. And you can see that it is quite fast. You know, I mean, here we count the efficiency typically with the number of passes through the data, right? So this is, I mean, the effort that gradient descent would need, right? One pass through the entire data. So here we measure how many times do we need to pass through the data to get some good efficiency. And here is a non-convex problem, and here is a phase retrieval problem. I will not go into detail, which is, you see here that you have a polynomial of fourth order. So you need this relative smoothness condition, and you need this Bergman distance in order to have a constant step size. And coupled with this LBFGS and line search on the envelope function, you obtain, you know, you make these algorithms behave practically because, and reliably, compared to what they do in the first order case without using any online precondition as we view this LBFGS type of directions, right? So basically, without those, the algorithm is pretty useless, right? So it doesn't do much. Okay, I have 4 minutes to cover Douglas Rafford and Admm, and I will only cover it very basically. So again, we have the same problem here, f plus g. Now we have a different algorithm, right? And this algorithm is in fact connected with the alternating direction method of multipliers. We will see how. And the algorithm now doesn't use any gradient information. It uses prox for both functions. So first it does a prox of f, then a prox of g at this point, and then it linearly combines these two proxies to get the next iterate. And here we have a new parameter, which is the relaxation, let's say, right? And of course, if the algorithm stops, we want it to stop at a point which is a necessary condition for optimality. And indeed, you can show that whenever this guy is equal to that one, then this is a necessary condition for optimality. So, but again, we have this, you know, root finding interpretation of the problem, or fixed point interpretation of the algorithm. And, you know, on this interpretation, you can develop convergence analysis in the convex case. Whenever f and g are convex, then basically you can show that Douglas-Rafford splitting converges for any gamma, for any step size. Now there is no restriction on the step size, as long as it is positive, and lambda, you know, being between 0 and 2. And this result doesn't require any smoothness on F or G, but it requires convexity. And convergence analysis is heavily based on convexity because it is, it shows that basically, roughly speaking now, that, sk plus 1 minus a star, which is a fixed point, which corresponds to some sort of global minimizer. So this guy decreases at every iteration. So its Lyapunov function is its distance from the solutions, from the global minimizers, let's say. But for non-convex problems, of course, we cannot have such a thing because they might converge to local solutions. However, Douglas-Rafford and especially Admm, which is the same method basically, are typically used as heuristics for non-convex problems, even mixed integer problems and so on. So we try to put some theory on the convergence, but of course we need to limit the scope, and so we need to assume that F has Lipschitz gradient here, right? So then basically you can show that you can write the algorithm as a shifted version of the proximal gradient method, where basically the second step corresponds to exactly the same proximal gradient step or majorization minimization. But the thing is now, instead of U here being the previous iterate S, it is basically the prox of S with respect to F. Right, so it is like a shifted forward, backward, proximal gradient iteration, and at the end you do also some averaging. But if U was equal to S, then this would become exactly, and lambda was equal to 1, then this would become proximal gradient method. Right? So then we can define also this Douglas-Rafford envelope. And in fact, we can show that it decreases along the trajectories of the method. So this envelope has also these nice properties, continuity and sometimes differentiability. The problems of minimizing phi and the envelope are somehow equivalent after you pass it through this prox. And then, the interesting thing here is that one step of Douglas-Rafford method does not decrease the true cost, unlike gradient descent or proximal gradient descent. So, but it decreases the Douglas-Rafford envelope, right? So, indeed, the only way that we have found so far, and many other people, is by using, at least implicitly, the Douglas-Rafford envelope to analyze global convergence of this algorithm, right? Without any extra assumptions like which involve the global minimizers. So then you can show convergence for a range of gamma and lambda, and in fact you can do the same trick with Panos to obtain a faster convergence rate in practice and in theory. And now what's the connection with the alternating direction method of multipliers, which is typically used to solve these problems? So it is this algorithm over here. Right, so you minimize the augmented Lagrangian with respect to X, then you do a dual update, and then another augmented Lagrangian minimization with respect to the second variable. So this is a problem in separable structure. Basically, you can show that this is exactly Douglas-Rafford splitting to this problem over here, right? And this doesn't require any convexity. Usually, people show that Admm, or they use the fact that Admm is equivalent to Douglas-Rafford splitting applied to the dual. But in order to say something meaningful about the dual, you need convexity. And here we don't assume convexity. So interpret it as Douglas-Rafford splitting to the primal for some formulation which involves this so-called epicomposition or image function. Right? And then we can employ the results that we have so far and see when we can guarantee convergence of Admm under basically this function being, having Lipschitz gradient. Then we can guarantee convergence for beta, the penalty parameter in the constraints of the augmented Lagrangian now being large enough, right? Not small enough. So you need large enough, you need enough regularization for non-convex Admm to converge. Some experiments to compare the nominal version with you can see them later. So I think that's all. let me mention here this, first of all, let me thank, because this is more important, thank my collaborators, right? Most of them now, they are dispersed in other places, but they did most of the work that I described. And also leave here the software that corresponds to what I presented. And I think we are a bit out of time, but now it's lunch break, so you will have plenty of time to rest. But I will be around, of course, to answer any questions.
Yeah, thanks. Thanks, Panos. It's really interesting talk. The idea of generating the function to some different envelope function and apply classical results on the envelope is really interesting, especially the Panos algorithm.
Okay, thanks.
Yeah. For the audience, does anyone have questions? Please speak out.
You can also write in the chat if you are shy.
Timid. If you are timid, you can write on the chat as well.
If no one asks question, I want to start.
Okay, sure.
Yeah, so thanks a lot, Panos. So I have a simple question actually. See, normally if we use Admm to solving the non-convex problem, so currently I don't think it's new, but normally they use this, how to say, it's called linearized Admm or linearized proximal Admm. So in principle, we think about one is a non-convex smooth term, another one is convex, could be non-smooth term. So then the people, they use this linearization of this non-convex smooth term, but different from the standard Admm, they have an additional prox term with respect to the previous iteration.
Indeed, yes.
Yeah.
And they can show that that it converges also in the nonlinear setting, right? So
yeah.
So
and
the
they have the
is,
convergence rate. I think they can show the y over k convergence rate.
Sorry, convergence rate. I think,
yes, they have the sublinear convergence rate.
Yeah, I think for all these methods, the standard convergence result is that the fixed point residual, let's say, the square norm of this goes to 0 with rate 1 over k, right? So that's which is the same as a gradient method. As gradient descent.
Yeah. So I got a curious that for this linearized proximal Admm. So what's this relation between it and the standard Douglas-Range-Fold splitting? I mean, so
yeah, that's a very good question. That's something that we have been studying recently, I would say. So you could let me provide a hint. So there are versions of the Bergman Douglas-Rafford. So basically, where you replace the quadratic term with a Bergman distance. So if you carefully choose the Bergman distance, then you can come up with a proximal linearized Admm. How is it called, right? So it is a matter of basically killing the nonlinear term corresponding to the smooth function with its linearization. So if you carefully choose the Bergman distance based on what I showed here, you will come up with the algorithm you just mentioned. So this means that you can perhaps do also this type of tricks with the envelope functions that I presented here.
I see. Okay, so it highly depends on how you pick this Bergman. The function in the Bergman.
Yeah, so this Bergman distance gives you a lot of flexibility, and you can do many things.
I see. Okay, so I have a second question about your algorithm, Panos. I think this algorithm has been also used. You have a collaborator called Alex from the Ford Center in Germany.
Yes.
You apply it.
Yes,
I talked to him before, so I think it's quite powerful. Since his problem is super expensive to solve online.
Yes.
So I have a simple question. So about this Panos, I think it's a primal method. So you don't have the due here. So if you want to try to do maybe like a standard primordial distributed algorithm design, so how to design this line search? I think the most how to say the beautiful and the tricky part in the Panos is the line search. So it always works for any D. So the direction you pick, you can pick any D. So I'm curious. So if this kind of framework applicable also for dual. If we solve the dual problem, can we also apply this kind of line search and how to design this kind of merit function? You call it phi in your slides. So
yeah, so basically we have a paper where basically we show how does the envelope look in the dual. So when you have a problem, you know, so when you have a problem on this in this separable structure and you apply and you go to the dual and you apply proximal gradient, then basically the envelope becomes the augmented Lagrangian function evaluated at some specific points. Right? Now, of course, whenever you do distributed implementations, as you said, doing a line search is tricky because somehow you need global information, right?
Yeah.
So yeah, I don't know how to do this. If you have some idea, I would be happy to discuss it with you.
Oh, okay. Since Yingzhou and I has thought about this problem for a while, we didn't find a proper solution.
Indeed,
actually, we are thinking that for the dual update, we can come up with a convergence dual, but for in Panos, there is an interesting thing. You have a direction D that really accelerates the global convergence, local convergence. But for us, the problem is that for dual, we don't know how to generate such thing if the problem is non-convex.
If the problem is non-convex, yes.
Yes.
Yeah, the most interesting must be non-convex thing, because for convex, there are many works that we don't want to reinvent something that already existed.
Indeed. Yeah, that's a good question, and I'm afraid I don't have an answer at the moment. But keep me posted if you find anything. I would be very interested to.
Yeah, we are searching for the solution now.
To see it.
Okay. Thanks a lot. Yeah. Okay.
Thanks a lot, guys, for the invitation, and I hope it was somehow useful to the students. Although I might acknowledge that it is not exactly on the topic of the summer school, but it is related to this first session, right?
Yeah, actually, the final problem you have where you have a consensus constraint, that kind of problem is commonly encountered in transportation system and other things. The issue is that probably the mathematical formulation is a bit really abstract, but that's why we need to have the abstract first day, and then in the last 3 days, some other speaker will try to translate the abstract math into some more engineering practical viewpoints.
Okay.
So
you have a good plan then. Okay.
Yeah, we hope that our plan works out.
Okay.
So we hope after this summer school, more people can use Panos.
I hope as well. That's why I also put all the links here, so you can you can test those. Okay.
So
thanks a lot.
Sorry, last simple question. So your Panos currently implement in. So you have the interface for different languages, right?
Yes. In fact, yeah. I mean, we haven't settled with one now. In fact, there is a new student who is doing a very good implementation in C++, which will be used in all other languages. And we have also found a way of making it more robust, and we have improved it greatly. But I still we didn't have time to prepare results presented in this presentation.
Okay. Thanks a lot. Have a nice afternoon, and
you too. And I will see you also later in the Gather Town, where I might pass by.
If you pass by,
I will try to
have
pass
further
by.
discussion. Okay.
Thanks a lot.
Bye.